Okay. Good evening, everyone. I am Nilmoni, a research scholar at IIT Kharagpur, and so today I will discuss something about legendary functions, and then Bessel functions, and then Sturm-Liouville problem, and yeah, and then we will see what is a vibrating string and regular Sturm-Liouville problem, and whatever we have learned from last week. Okay, and that will help you to solve your assignment problem. Okay. Hi. Yeah, good. No problem. I can- Okay. I don't know what is the problem. Okay. Okay, so first let us discuss whatever we have done so far. Okay, and then we will solve some problem. Okay. So are you solving assignment or not? Oh, okay, okay. Okay, first we will see one theorem. Last day we discussed what is legendary polynomial, some properties of legendary polynomials. Now, in general, we will see. Okay, so one important theorem. Basically, it is about legendary differential equation. Okay, and not necessary the solution for legendary differential equations have to like legendary polynomial. It may not be polynomial, it can be any function. Okay, so the theorem is basically interlocking um, of zeros of legendary functions. Okay, um, yeah. The theorem is suppose 0 less equals to p less than q. Okay, and your yx, zx are respective. Obviously, we take non-trivial solution of this two differential equation. Yx like yeah, 1 minus x square yx y dash x. Okay, y dash x whole dash plus p into p plus 1 yx mm, mm, and similarly 1 minus x square z dash x dash plus q and q plus 1 zx equals to 0. Okay, so you can see this yx is a solution of this legendary differential equation, and zx is solution of this legendary differential equation. This both are legendary differential equation. Okay. Okay, and then what is the conclusion? Then between two. So actually, we are trying to locating the zeros of legendary solution of legendary differential equation. Okay, we are trying to locate the zeros of legend solution of legendary differential equation. So yeah, so two successive zeros of yx, there is at least one zero of zx. So here the difference is p less than q, and here p and here q. Okay, and remainings are like same. Okay, this is the theorem. The proof you can check from lectures video. Okay, as well as notes. Now, okay, anyone want to join? I don't know. Mridula want to join every day, but okay, I don't know. What is the problem? Okay, and next, generating function for the legendary polynomial. Hi, do you know about generating function? What is generating function? Yeah. Simply, actually, we deal with power series. When do we deal with power series? So uh, then only we can think we can talk about generating function because this power series, right? This is power series n t to the power n, right? But actually, this is nothing but a function of f t, right? So this is the generating function actually. Okay. So you know, right? 1 by 1 minus x is so this is the generating function for this series. Of course, x less than 1, mod x less than 1. A geometric series, right? Yeah. So this is the generating function for this series. So here n is your 1. Okay. Okay. So now similarly we can talk about the generating function for the legendary polynomial. Okay. Wait. I think. Okay. Oh, actually, something. What is the problem, bro? Okay. It is not visible, right? Uh, hmm. Okay. So the theorem is n equals to 0 to infinity t to the power n pnx. Now this is series, right? So I'm writing t to the power n in font. Uh, okay. And this is root 1 minus 2xt plus t square. Okay. But how to prove? Did you check the proof? Okay, okay. So, actually, by yeah, like reverse way we can show this. Okay, so first write this is vxt, right? This function 1 minus 2xt plus t square. Okay, and obviously this gives some function series of function like this. But we claim this Rnx nothing but Pnx. Okay, for all n equals to 0, 1, so on. But how to show? Okay. One thing is this like this series is convergent or not? Okay. So this is basically uh, this was discussed in previous week. Okay. So this is actually absolutely convergent series. Okay, absolutely convergent on this Rnx. This is a polynomial of degree n. Okay, okay. So I am not going to discuss this proof. Okay, so you can check from lecture notes. Okay, if you are interested, and if you start, then you can ask me. Okay. Mm-hmm. Okay. Next, one interesting identity: Fourier legendary series. Okay. Fourier legendary series. So this is like e to the power itx can be written as n equals to 0 to infinity to n plus 1 I to the power n. I means iota, okay, and root pi by 2t times jn plus half t pnx. Okay. Okay, you know about jn plus half t. This is a Bessel function. Actually, here jnx, this series n equals to 0 to infinity minus 1 to the power n factorial gamma n plus. Okay, I should write this jp. Uh, okay, n plus p plus 1, sorry, x by 2 to the power p plus 2n. Okay, this is Bessel function. Okay, and this identity you can prove by induction. Okay, uh, by taking alternative form for this JPX. Okay, now this JP has Laplace integral representations. Okay, Laplace integral representations this instead of jn, write to jpx 1 by pi 0 to pi cos x sin theta minus p theta d theta. This is a similar formula for p and x due to Laplace. We have seen, right? Like this theorem was there for n greater equals to 0. Of course, non-negative integer pn x 1 by pi read 0 to pi x plus minus cos theta and d theta. Okay. This you can prove using some trigonometric identity and recursion formula for p and x. Okay. And, this has another integral representation. This is called Laplace second integral representation. Also x greater equals to 0 here. Laplace's second integral representations. And for n greater equals to 0 and x greater equals to 1 here, pnx is 0 to pi d theta x plus root x square minus 1 cos theta n plus 1. Okay. Now let us take one. So this integral representations so that this is basically a formula of C Newman. So the formula is basically just so that okay, limit intending to infinity Pn cos x by n equals to j naught x. Have you seen this? Yeah? No, no. Okay, okay. Okay. Oh. Um, Actually, we have to use this one only, this integral representations. Okay. Okay, so what is PNX? What is PNX? PNX is your 1 by pi 0 to pi d theta cos theta n plus 1. Okay, so this is cos x by n. Oh, right, so 1 by pi 0 to pi. So instead of x, so you have to put cos x by n, right? Uh, Actually, I don't know which one we should use. Fast integral, not okay. So do you have copy right now? Are you trying this? 1 by pi 0 to pi. First one I have to use actually. This x plus root x square minus 1 cos theta to the power n d theta. Okay, now Pn cos x by n, 0 to pi cos x by n. Okay. Oh, what is this actually? Cos square x by n minus 1 cos theta d theta. This is 1 by pi 0 to pi. Mm, yeah, we can take common cos x by n to the power n, then 1 plus. Okay, from here you are taking common, and root minus 1 is your I, right? And this will be 1 minus sec square. Okay, so that is basically root under tan square x by n, I times. Right. Tan square x by n cos theta to the power n d theta. So cos x by n 1 by pi 0 to pi 1 plus I tan x by n cos theta to the power n d theta. And now one thing, limit tending to infinity cos x by n to the power n, no, yeah, to the power n. That's actually what limit n tending to infinity n, so exponential power n uh, log cos x by n, right? It is 0 1. That is you can think like this. x is here, so cos x by n. So yeah, cos x by n, right? Can you find this in this limit? Cos of x by n to the power whole to the power n. Yes. Can you find this? Yeah, you can actually use L hospital rule, right? Yeah, yeah. Hmm. Yeah. So I'm writing like limit intending to infinity exponential, not right. Yeah, n log. Okay. Hmm. Yeah, actually, I know. This we can by truncating we can do that. Okay. Hmm. Okay. Do like that. Okay. Limit intending to infinity. So your cos x like this, right? X square by 2 factorial. Okay. So n time log of this 1 minus. So yeah, that is basically your x square by 2 factorial n square, right? And this is your log x. What log x? This is x minus x square by 2 plus and so on, right? And that is basically your limit intending to infinity n. This first term is this, so all are like negative. So this is negative x square by 2 factorial n square. Okay, so 1 and 1 n cancel, so that is limit is 0, and that is e to the power 0, yeah, that is 1. Yeah, so your guess is correct. That should be 1. Yeah. Yeah, good. And okay, so you are getting this is 1, and you have to like think about this only. Okay, now focus on the integral 0 to pi 1 plus I tan x by n cos theta to the power n d theta. Now if a lambda goes to alpha, then by L'Hospital rule 1 plus lambda a lambda to the power 1 by lambda, that goes to e to the power alpha. That is correct. Again by L'Hospital rule. Okay. This limit actually works. Okay. So this is true first. Yeah, a lambda goes to alpha. Okay. Hmm. Okay. So then using this, yeah, just you consider a lambda. This is this is your basically I cos theta. Okay, I cos theta, and then so this limit finally Pn cos x by n. This is 1 by pi 0 to pi. Okay, so first limit is 1, and this is nothing but so your alpha is basically x cos theta. Okay, e to the power alpha, because you know here this goes to actually this sequence goes to only cos theta. Okay, so this is e to the power I x cos theta and d theta, and this is nothing but your j 0x. Okay, okay, now next see the another thing. Okay, so like do you know about Sturm-Liouville problems? Have you heard about this? Sturm-Liouville problem. Sturm-Liouville problem. Sturm-Liouville problem. Okay. Yeah. Okay. STURM. Sturm. No, 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 no. Both are different. Those are different. Two different persons. Yeah. 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 See. This is basically you are given a differential equation like this. Lambda rho x. This is any function of x. Okay. And y equals to 0 with your boundary condition y0 equals to yl equals to 0. Okay. Uh, then it is called actually boundary value problem. Okay. And we have the target is to find the non-trivial solution. Okay. just for example, you check this problem. Plus lambda y equals to 0, y0 equals to 0 equals to y1. Okay, then actually the non-trivial solution is, you know how to solve this. Okay, you you know very well. Y equals to a cos. Yes, yes, yes. Yeah. uh, so now if you put here y0 equals to 0, so you will get a equals to 0 immediately. And this condition y1 equals to 0 gives you b sine root lambda x equals to 0. Sorry, root lambda, not x, only. And from here, what is the choice of root lambda? Just you consider here, from here either b equals to 0 or sine lambda is 0. So just for non-trivial solution, you consider b not equals to 0. Then sine root lambda equals to 0, and which implies root lambda equals to n pi. N is your integer, right? So lambda equals to n square pi square. And from here, so your solution is non-trivial solution b times sine n pi x. Okay, this one is your non-trivial solution. And also, this is called eigenvalue. So you can find also eigenfunction. This one is the eigenfunction. Okay. So one theorem is there, orthogonality of eigenfunction. So for the boundary value problem, 0L. So one thing I forgot to mention, this is actually Dirichlet boundary condition. And one another condition, this is called Newman boundary condition. That is y dash 0 equals to 0, y dash L equals to 0. This is called Newman boundary condition. Okay. And yeah, so my statement is for the boundary value problem on 0L. You consider this with either Dirichlet or Newman boundary condition, the eigenfunction corresponding to So see, here these are eigenvalues. Okay, these lambdas are eigenvalues. Corresponding to your to distinct eigenvalues. So these eigenfunctions corresponding to distinct eigenvalues are orthogonal. You know what is the definition of orthogonal function? Orthogonal on 0 1 with respect to the weight function rho x, that is 0 to L ux vx rho x dx equals to 0. Okay. So if you have distinct eigenvalues, then you will have orthogonal. So the eigenfunction corresponding to distinct eigenvalues are orthogonal with respect to the weight function. So weight function, this is same as this rho x. Okay. So there are many theorems regarding the simplicity of eigenvalues. This To each eigenvalues of the BVP, boundary value problem, and so with respect to Dirichlet boundary condition, there is only one eigenfunction up to scalar multiples. But now I think we can solve some problems. Okay. Uh, okay. This value of. Hi, can you solve it? Function of x and t. V half comma 1. Yeah. Yeah, correct. Yeah. No, actually, that is not. I want to find. Okay. So already just we have seen, right? N equals to 0 to infinity t to the power n generating function of legendary polynomial. What is this? 1 minus 2xt plus t square, right? Just we have seen, right? Can you remember? Yes, 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 yes. Let's see. This is you can. So this theorem is basically this. This is theorem. Okay, let me prove it. Okay, how to do it. Okay, so consider this vxt 1 by root 1 minus 2xt plus t square. So yeah, then it can be expanded in the absolute convergence series. Right, n equals to 0 to infinity Rn x t to the power n, and Rn x your polynomial of degree exactly n. So now if you like see if you if you square it, okay, like this, we will have this 1 minus 2xu plus u square 1 minus 2xv plus v square. So j equals to 0 to infinity, k equals to 0 to infinity, rjx, rkx, u to the power j, v to the power k. Okay. And now integrating both sides with respect to x. Okay. If you write integrating both sides with respect to x, once a similar computation will give you. Just you can write like this: uh, x minus u square plus yeah x square. Yeah, x minus one. So yeah, 1 minus 2xu plus u square can be written as uh, x square, not x square. Actually, 1 minus x square plus um, x minus u whole square. You can write like this, okay? And and then you can find this integral like this. Sorry. And if you integrate here in right hand side, then uh, okay. Hmm, minus 1 to 1 and rjx, rkx, okay, and here u to the power j and v to the power k dx, and in the left hand side, if you like calculate, so you know the series expansion for logarithm of 1 plus x, and that will give you 2 u to the power n v to the power n 2n plus 1. Okay, and that is equals to this sum j equals to 0 to infinity, k equals to 0 to infinity, u to the power j, v to the power k minus 1 to 1. rjx rkx dx. And now comparing the coefficient of u to the power j v to the power k. Okay, u to the power j v to the power k. Then you will have minus 1 to 1 rjx rkx dx equals to 0 if j not equals to k, and minus 1 to 1 rjx square dx equals to 2 by 2j plus 1. And now by, so this is same as legendary polynomial. So by orthogonality lemma, so rjx is pjx for j equals to 0 1 2 so on. Okay, so finally your vxt is what? Root under 1 minus 2xt plus t square. So v half comma 1 is root 1 minus 2 into half into 1 plus 1 square, that is root 1 minus 1 plus 1, that is 1. Got it? Now, okay. This is tricky. Related to your assignment, okay? Like, don't try like with another source. Uh, this integral hyperbolic, okay? Tan hyperbolic alpha cos theta and sine hyperbolic alpha plus cos hyperbolic alpha cos theta d theta. Can you find this integral? Yeah, 0 to pi. That is a range of theta, okay? Well, means like theta lies between 0 to pi. If you have any idea, uh, actually no, you have to think about like yeah, that is true, but you can solve it using your some legendary polynomial concept, Jacobi concept. Hmm. Yeah, actually, I just mentioned right previously. Okay, let us solve it. Recall the Laplace second integral representation for n greater equals to 0, that is integer of course, non-negative integer, and a real value x greater equals to 1, x square minus 1 cos theta. Okay, so here you can see there cos theta, this is cos theta. Okay, something related to this, right? Yeah, but so x can be put like sine hyperbolic alpha. Yeah, yeah, but this is not straightforward like this. So something is different, right? So yeah, that is no d theta is there. D theta is also here. But see. Now, if you derivative this thing like both side with respect to if you differentiate with respect to x in both side, then you will get the actual formula. Okay. Hmm. So what is Pn dash x? 0 to pi t dx 1 by x plus root x square minus 1 cos theta to the power n plus 1 d theta, right? Now 1 by pi 0 to pi, so minus n plus 1 and x plus root x square minus 1 cos theta to the power n and 1 plus 2x root over of 2 x square minus 1 cos theta. Okay, so that is minus n plus 1 pi 0 to pi and what is this now? 2 cancel, so x square minus 1 plus x cos theta and x plus root x square minus 1 cos theta to the power n d theta. Okay, so this integral 0 to pi root x square minus 1 plus x cos theta x plus root x square minus 1 cos theta to the power n d theta equals to minus pi n plus 1 times pn dash 1. Now put x equals to sine hyperbolic alpha and n equals to 1. Okay, then you will get the result. So this x square minus 1 is basically cos hyperbolic alpha plus sine hyperbolic alpha times cos theta. Then sine hyperbolic alpha plus cos hyperbolic alpha cos theta to the power n d theta. That is actually that is required, right? Oh no. Okay, something we have to do. Okay. Oh, one thing I made mistake. Okay, so here also x square minus 1 is there. X square minus 1 is there. So x square minus 1 is basically cos hyperbolic alpha. Okay, so that is 0 to pi. Your yeah, so 1 plus tan hyperbolic alpha cos theta and sine hyperbolic alpha plus cos hyperbolic alpha cos theta to the power n d theta. And actually, this is what we needed. Okay, this integral we wanted to like evaluate, and So n is 1. Last step? Yeah, yeah. So minus pi by 2 and p1 dash 1. And this is what like we already have proved in last lecture. So Pn dash 1 is half n into n plus 1. Okay, so P1 dash 1 is actually half into 1 into 2, that is 1. So that is only minus pi by 2. Okay, it was a little bit tricky, right? To guess how to do that. Okay, yeah. So in assignment, the one question is in assignment, okay, but that is not tricky too much, okay. But yeah, so here the question actually I made this question I made actually, and in the assignment, yes. Yeah, actually in assignment the question is straightforward. Okay, you can put here only instead of derivative. Okay, yeah, yeah. Now you can check. Okay. Letters. And now next problem is so that J half P L P R for only if P belongs to no, yeah, 2 to infinity. Yes. Can you solve this? Ah, do you have any idea how to solve it? You know about LPR, right? For okay. That is actually your so that is called essential bound, essential supremum of every x or some. Okay, okay, let us check. No, actually, yeah, supremum, you can say. Yeah, that is, yeah, yes, 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 yes. So we know that JPT, already we defined this. So whenever you put P equals to half, then 3 by 2, 2, now one thing n plus 3 by 2 is you can calculate this using properties of gamma function. Uh, okay, and putting this uh, okay, and 2 to the power 2n plus 1, here 2 to the power 2n plus half, and 3 to the power 2n plus 1, and this is root t. And now calculating this root 2 pi t, this sum. Do you know about this sum? No, no. This is the series of sine t only. Yes, 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 yes. So this your j half t is root 2, sorry, root 2 pi and sine t to the power root t by root t. Okay, and this is basically sine t and root t. So constant we doesn't matter. Okay. Uh, now, yeah, to come down. Okay. Oh, that is my mistake. Okay, sorry. Yeah, yeah, yeah. That I know. Okay. Yeah. Thank you. Okay. And uh, so now this is actually sine t root t. So what about p equals to infinity? Uh, so for t tending to zero, okay, this limit t tending to zero, sine t by root t. Okay, this is a 0 by 0 form, right? So limit t tending to 0 cos t 1 by 2 root t, right? And that is, this t tending to 0, 2 root t cos t. And this is 0. So there is no problem when t is near to 0. So we are getting finite value. Okay. So and for mod t greater than 0, yeah, then sine t by root t, this modulus, this is by 1 by root t, and this is actually bounded, right? Some constant. Okay. And so you are getting always this is always bounded, right? So I have written the definition of L infinity. So you are getting this function is bounded by something, and so your sine t by root t is in L infinity R, and that's why your j half t is in L infinity R. Okay. Uh, because yeah, that is away from zero, right? So uh, anything like whenever t is large, that is like goes to your, yeah, yes, yes, that's why, yeah. The problem is at t equals to zero, but at t equals to zero, that is finite value. Okay. Yes, 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 yes. And also uh, for, okay, so now limit, sorry, not in limit, integration r sine t to the power p divided by p to the to the power p. So I'm calculating like whether it is in LP or not, and p greater than 2. Okay. Okay. So see, similarly, uh, for t when t minus 1 to 1. Okay. When minus 1 to 1, so this sin t actually you can approximate like this. Okay. So in that case, t to the power p and t to the power p by half dt. So that is t to the power p by 2 dt. And this is absolutely fine. Okay. We just this is convergent. And now for t does not belongs to minus 1 to 1. So r and t belongs to minus 1 to 1. Okay, so that sin t divided by root t and whole to the power p dt, and then in that case sin t less equals to 1. Okay, and that is 1 by t to the power p by 2 dt. When this series is convergent, if and only if only p greater than 2, p by 2 greater than 1 only, so that is p greater than 2. Okay, then only convergent. So j half of t is belongs to L2, sorry, LPR mm, only if p greater than 2. Is it clear? Okay, so one more question. Can you solve this integral? Like, did you see this type of integral earlier? Yeah. Yeah, exponential. This is a type Gaussian type integral, right? Actually, see, if you see closely, this is a quadratic form. The Yeah, outside. The exponential of this thing and this is dx dy dz. So, did you study a quadratic form quadratic? It is in linear algebra. Okay. Now, actually, this gives a matrix. Okay, matrix. So minus two, minus one, minus two, five, two, minus one, two, two. Okay, so the matrix actually two is these are only for diagonal. So basically, this is that is x y z. So x square, y square, z square, and here xy. So but xy here also. So you have to like so 4xy. That's why minus 2 here, minus 2 here. Minus 2, so exit, so minus 1 here, minus 1 here. Symmetry matrix. And 2 here and 2 here. Got it right? Symmetry matrix. What is the eigenvalues? Yes, uh, real symmetric. Yeah. So what are the eigenvalues? So if you calculate eigenvalues, so one I am not calculating. Okay, so you can calculate like this. Okay. Yes. Huh. So this will give okay 117. Now important thing is that this is symmetric matrix, positive definite matrix. Okay, and so here your quadratic form is basically this is A is your matrix and X is your X Y Z and and one thing this inner product X Y is like this X transpose Y. Okay, and so this is one can write like this Py and P is orthogonal. Okay, so like we are writing X equals to Py. Okay, and then multiply P transpose A P Y and this is Y. Okay, now this matrix is nothing but the eigenvalue 117 rest are zeros. Okay, and now just your integration. So what was your integration? Exponential minus ax comma x dx, and this is r3 exponential minus pt ap y and y dy, and this is nothing but exponential. So this is your this integral. If you multiply with y, then it will give you minus y1 square plus y2 square plus 7y3 square dy. Sorry. Now here y is y1, y2, y3. So dy1, dy2, dy3. And now just you see simply r e to the power minus y1 square dy1, r e to the power minus y2 square dy2, r e to the power minus 7y3 square dy3. And that is nothing but root pi, and that is also root pi, and that is root pi by root 7. So your 2 pi to the power, sorry, pi to the power 3 by 2 by root 7. Okay, got it. For this type of integral, you can solve like this. Okay. Okay. Up to this, I have prepared, and if you have any, so you can ask. Yeah, 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 yeah. Exactly. With Fourier transform, okay. Fourier transform, Laplace transform, all are like connected things. Yeah. Eigen here. So this is quadratic form. So the corresponding matrix is this. Yeah. Second degree. Yes, yes, yes. That's why quadratic, right? That's why we call quadratic. Yeah. 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 Okay. Finding eigenvalue means yeah. That is the main thing. So x comma x, right? Here your this is a symmetry matrix. So this is diagonalizable. Okay. So that's why P is orthogonal, and you can write like this. Sorry. Yes. 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 Okay. So this matrix is like form. This matrix is formed with eigenvalue 117. Got it? We transform this actually. Yeah, not matrix decomposition. We have transform x first, then multiply with. So basically, transformation is your x equals to py. Okay, and then we are getting this, and this is nothing but the matrix. Uh, this this with eigenvalues this 117. Okay, got it? Yeah. Yeah, so basically, so then we are getting this matrix. Okay. And the corresponding quadratic form is this. So we are simplifying. Okay. And now exponential this. So you can like decompose like this because exponential of a plus b is e to the power a plus e in times e to the power b, right? This, yeah, yeah, right, right, absolutely right. Yeah, exactly. Yeah, yes, correct. Now got it right. Okay. Yes, eigenvalues. Yeah, exactly. Okay, then we'll meet next week. Okay. Yeah, thank you also. Okay. Yeah, 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 yeah. Thank you. Okay. Hmm. Thank you.